Okay, welcome everyone. Hope you've all had a good lunch. This will be session 3, Energy Systems and Advanced Tools. And we might as well get the ball rolling with Professor Jihong Wang, our keynote speaker from the University of Warwick.
Okay, can I get my screen sharing? Can you hear me?
Yep, we can hear you.
Okay, I just share my screen. Can you see my screen?
Yes.
Okay. All right. Hello, everyone, and thank you very much for the invitation to have a chance to speak at this event. So my topic today is about compressed air energy storage, and probably compared with other technology. And this technology is not that popularly mentioned in the research area in the UK at the moment. And so I'm trying to talk about this technology from a different angle. Okay, so my talk will start with background and then introduce what's a current development in compressed air energy storage, and finally summary. And this is probably well-known fact. And since 19th century, Tesla won the battle. We have been using this alternating current system for until now. So for the alternating current transmission, at the very beginning, and initiated because it's transformer, they can get high efficient energy transmission, reduce energy loss. And now, with more renewable energy integrations and the flexibility from the demand side, and the challenge for maintaining the grid balance become enormous. So this is a screenshot from National Grid Statistics website. It's on 10th January in the afternoon, early afternoon. And if you look at this at this moment, and the frequency is 49.982, that means that moment, the generation is slightly lower than the demand. Then after 5 minutes, and the frequency changed to higher. That means after all the strategy of balance or demand change, and at this moment, the demand is slightly less than the generation. So this is not just national grid in the UK and all the countries and everywhere, and to maintain the grid balance, and that's something must be done. So the job for the grid operators, they constantly they're trying to bring this balance to maintain our transmission of power grid frequencies around 50 Hertz. If this value be away from 50 or from rated value too much, it may just simply cause the whole power transmission system collapse. And by doing this, to maintain this balance, it's really come with a cost. This is one particular example. That's, for example, on 28th December 2020, last year, and National Grid spent £3.96 million on that day, just for balance the whole grid. And this gave the breakdown, the cost, where those costs from. And certainly, we can see something, and energy storage also start playing a role in this particular plan. And for the 7th January this year, and that day cost 8.2 million. So it's really come to the cost. And probably from estimation, around £2 billion needed to just try to maintain the grid balance. For example, if we forecast the generation and is away from the real generations, and you have to pay high price to buy the peak value, peak time generation, to pay very high value to buy extra generation on board. And if sometimes you generate too much, you have to pay money to the generator to not generate. So that's all the cost from. So this why in we can see that in recent years, energy storage becomes more and more valuable and becoming a very hot topic, apart from transportation and portable devices. Also, there's a great storage in the power sectors. And from the power sectors to balance the demand and the generation to increase the grid flexibility, and the energy storage plays role either can on the user side to regulate the demand and then to save money and to help with the grid balance, or on the generation side to use energy storage to regulate their generations and to try to close to the demand side to reduce their cost and also delay the investment on new or enhanced infrastructures. And also they say this annually increase in energy storage and in either on the generation or grid side and also behind the meter. That means normally for the behind the meter on the distribution or user side. So they both sides start growing annually and trying to catch or into this market, catch up revenues. And also we can say that energy storage globally in installation until 2019, that's how much been installed. And in all the installed energy storage for the grid service, and this lithium-ion battery probably is a dominate. It's around the world, it's dominate, and also in China, it's dominate, and in the UK also it's dominate. They probably very often see the news and see some storage project and just started or get funded or get investment. So anyway, in the UK, energy storage installation increased rapidly, around the world increased rapidly. But when we look at the installations and in recent years about energy storage, probably, and we can say this, all this project, and mostly for commercial project batteries. So definitely the batteries and is a winner in recent years. However, if come to the net zero emission target or goal, if the renewable energy increases to 50, 60, 70, 80%, then what's going to happen? If and this is enough. So one particular example is last year, and UK demand is this orange line. And all the renewable energy from wind and solar put together is this blue line. If you look at this line, look at the various gaps. If you come to this such kind of gap, a few days, and we don't have much renewable energy generations, and can we still use batteries? And this becomes a question. It's not just about technology. It's actually a cost. And current for, if we look at the battery into the energy storage market in grid balance, they really catch up the high value market for grid balance, for example, frequency response, is worth quite a lot of money. if you put into such kind of large capacity, long-term capacity storage, the market value currently is much, much lower than those high frequency ones. So if even they have the technology, they can install massive batteries into such kind of a space, can store a couple of days or few days, and larger scale to power 50% of a national need. However, probably the battery wouldn't have the market position like today in the high-end value frequency response sectors. So in that case, we need to look at a long-term storage technology. And this morning, Christos has given the presentation and mentioned the various long-term storage technologies. And here I probably just mentioned particular about compressed air energy storage. For compressed air energy storage, it's not a very new technology. It's already in the history for a very long time. And the concept is very simple. During the peak time, during the off-peak time, and use electricity generated and to compress the air into high pressure and store in the reservoir. During the peak time, they need more electricity, and the air is released and drive the turbine and then drive the generator to generate electricity sent back to the grid and to meet the need. The very first one was built in the world. It's 1978 in Germany. It's Hutty compressed air energy storage. And for this particular system, we use a gas turbine burning natural gas to boost the power to give additional energy and to boost the power. And another thing is use the compressed air to increase the power of a gas turbine, but anyway, that's mixed. And the compressed air is stored in the salt cavern. So we visited this power plant. It was built in 1978, commissioned in 1978, and now still in operation, and really trying to compensate the power fluctuation and from wind generation locally, and still in operation. So the cavern, the power plant used is a cavern created by some other salt industry when the engineering salt left this hole underground. So they just cheaply rent this cavern and stored compressed air. A second largest scale compressed air energy storage is the American Macintosh plant. It's something slightly improved with this plant. They put a thermal storage and reheat the air and then to recover some kind of a heat loss. So that's makes the efficiency slightly high. And that's the plant, and it's still in operation, built in 1991, still in operation. Then look at this, both compressed air energy storage power plant, they have a common feature. They both use a fossil fuel. And so now the third generation of compressed air is current research really focused on the system does not use any fossil fuel. So during the compression stage, the heat captured and stored, and then afterwards will be reused and then for generation to boost the power. And compressed air energy storage has been criticized for a long time due to low cycle efficiency for both a Hutty and Macintosh power plant. the energy store, the whole round trip efficiency probably just no more than 46%. So for this new generation to make this technology acceptable in the market, and the effort has been made in trying to improve round trip efficiency. And also because the low energy density of compressed air, and the effort also made trying to find how to store larger scale compressed air in the feasible and cost-effective way. So we had a EPSRC funded project, and it's through the grant challenge, energy storage grant challenge, and part of probably 40% of the grant has been used trying to study compressed air energy storage. And as we mentioned, the research focus really on this both aspects. One is how to improve efficiency, and another is how to find the feasible cost-effective storage, in particularly in the UK. And I just simply borrowed one slides from this morning's Christopher's talk, and about the recent study about the cost of the storage. And from this study, already quite clear to say if you store in the salt cavern, and the storage cost will be much cheaper, has much lower price. But certainly this is restricted by national resources. If for some countries, they just simply don't have salt deposit, and that means no way they can engineer in salt caverns and to store and compress air energy storage. And however, UK is very fortunate, and through our study, and we work with British Geological Survey, we look at the whole UK salt deposit, and also examined the cavern or existing cavern. They are currently used to store natural gas, and to work that out. If we use a 1% available volume, salt deposit volume, and we can store 100 terawatt hours energy. And currently in the UK, we use 300 terawatt hours electrical energy. So it's almost a third of the energy, and for the currently total national usage. And so with this analysis, geological analysis, and they examined the deposit, and we developed a kind of a software tools. We can simply put the geological condition into it based on the software behind it, all the modeling. And we can do the calculation based using, because when you store air into it, when you try and extract energy, it doesn't mean you can extract 100% energy. Based on all this calculation, that's we got these conclusions. And all these informations and already become a data file in the GIS geography information system stored over there, and different layers. And in the UK, and the deposit of the salt. The deposit of salt, we made a map, and the salt deposit and also wind generation to see if they have a coincident correlation location. For example, we don't want to have a storage in the south part of UK, but the generation is in north. We mapped our salt deposit with onshore and offshore wind generations. They probably in the very close locations. And also for the salt deposit, and there are different height. Some height of deposit you cannot use. So through the whole calculations is through this available and useful, feasible height of the salt deposit, and that's the results. So from our study, and we believe UK has a great capacity and great potential to use compressed image storage for long-term and for long-terms and larger scale and the storage. And to make salt cavern, actually it's you just drill a hole and put water and dissolve the salt and extract the salt, the dissolved water, and then form the larger cave. And so that's compared with porous and the rock storage, and it's the engineering the storage volume has a much lower cost compared with them. So that's one aspect, and through our project, and we believe UK has a great potential in the resource of storage. In terms of efficiency improvement, and we did a system level of study. We developed a software tool and use MATLAB and Simulink. We build a library and all the components of the compressed energy storage and put it into the standard library and become the simulation tool. And when we try to do whole system dynamic analysis, and we can simply get the components into formulate to the simulation program to do the complete process simulation. And this has been put into a website called estoolbox.org. And so you can log on to the website and you can find the categories of the software and tools. And then you can open each and to get the help file and get the program. Also, you can download it as a whole library of all the package. And there's a demonstration video to show how to use this software too. And so that's another work we did about compressed energy storage. And with the software we developed, we helped with a potential UK project in Northern Ireland trying to calculate the storage capacity and verify their results. And also use these tools. We participate one particular 10 megawatts compressed air energy storage demonstration project in China. So that's the project, and build is overground storage, 10 megawatts and 20 megawatts hours storage capacity. This is a third generation adiabatic storage trying to store heat and then release it releases some more energy when come to generation process. And so when they started this project, the energy efficiency, round trip efficiency, the highest is 46%. And we finished this project 2 years ago. And this plant has demonstrated a round trip efficiency from electricity to electricity, so 63.6%. And this project is currently in generation, connected with the grid. And another project we visited is in Switzerland called Alakes, and they use abundant tunnel and sealed to store a compressed air. It's not very large scale and less than 1 megawatt. And so, but from the report, from there is a 72% round trip efficiency. And also from this project, its claim has the lowest capex per kilowatt hours for storage. And so that means for compress that energy storage. And there are quite a lot of projects really on the way to improve its round trip efficiency and also explore various storage capacities. And recently, they
5 minutes left now.
Okay, recently they did a kind of a survey, and around the world there are around 3.5 gigawatts power capacity compressed air energy storage demonstration or commercial project ongoing, and the highest power rating is 100 megawatts, and then the efficiency is aimed trying to through the larger scale to achieve 69 or over 70%. So that's around the current situation about the compressed air energy storage development. And then come to the summary and compare with come to larger scale and long-term compressed air energy storage. And even in 2014 is probably lowest. Now still has its a cost advantage, low cost advantage. And however, in the world, there is also larger storage capacity is over 6,000 terawatt hours storage capacity around the world. And however, there is a number of compressed energy storage and project has to be terminated. For example, RWE Adela project, and due to unclear economical viability and stopped. And Northern Ireland, and at the very beginning, is really quite promising, but after a few years, it's terminated because they passed the public consultation stage about this store air on the ground or the local area. But the planning permission took a very long time, and the company gave up after spending quite a number of £1 million on the project. So my personal opinion, and compressed air energy storage and has a low cost, and but in the current situation, it's quite difficult to attract the investment. And why? Because energy storage, because the energy type, and it's in the low value market, low value end market, and the battery, because for faster response in the high value market. For example, if you put 1 unit battery storage, you can make 10 pounds. But if you put compressed air energy storage, you probably can only make 10 pound revenue, 1 pound revenue. So that means it takes a long time to get your investment back. And also people compare with batteries still have the low efficiencies. And the battery can be any scale, small and small scale or large scale. So if you invest on the small scale, you have a lower risk. But the case, only when you has a larger scale, it makes sense. So that'll be a large investment, but it take long time to get money back. And 2 years ago, I worked with a company trying to invest. The company got money trying to invest to build 30 megawatts compressor air energy storage in the UK. And even I don't understand the finance that much, but I saw the financial analysis sheets from the company after a long time, and they gave up because they probably start seeing their money based on current electricity market. They probably see their money back, and after 15 years, they start trying to get some money and to recover their cost. So that's why I have to stop. So I think
1 more minute now.
Yes, I finished.
Okay, cool.
Yeah. Just say the technology itself is one aspect. Market and application probably wouldn't allow all the good technology then or has their position.
Brilliant, thank you very much. That was really interesting. I particularly like the MATLAB library. That looks really interesting. I might have to go and check that out. Can anyone put? Okay, someone's already put a question in the chat. With our existing and future salt cannon capacity and R&D activity in adiabatic case, is the UK in a position to demo case? And if so, what is the next step?
Okay, and the UK and did and they did have such kind of initiations as a five or 7 years ago, and the Gate Electric and started trying to put a compressed energy storage project in Northern Ireland near to Belfast. And initially the project went so well, and there are quite a lot of investors and watch the project and probably want to buy the project if get permission or invest on it. But the whole process took a very, very long time, and as end and it stopped. But now, that's something I feel it is a technology to have potential for long-term storage, but difficult to get people's attention. And especially after that project, I noticed it's not just from market, also from the planning permissions, from the public perceptions, and the various aspects. And especially the money is quite very investment to get money back, very important for private sectors. If you look around the demonstration or project around, probably China is dominant. But if you look at the money, there's money from, most of them from the various project state-owned companies or from the government. So that's how to get. So it's still uncertain, and mainly who want to invest in this high-risk area if we don't see the money come back soon.
Brilliant, thank you. Okay, so just to make sure that we stay on track, if you have any further questions, please put them in the chat, and I'm sure Professor Jihong can acknowledge those in the chat as we go along. Thank you very much, that was really, really good.
Thank you.
Now we move on to Timothy Hutty from University of Southampton, delivering a presentation on energy storage with reversible solid oxide cells for microgrid applications.
All right, can you hear me, first of all?
We can, yes, and I can see
Great. You. And screen should be coming up.
Yep, that's come up.
Yep. So first thing I should say is that I am in fact University of Sheffield principally, which is a mistake I maybe should have corrected on the conference program. But yes, I belong to the energy storage CDT here at Sheffield. And the title for this talk is Long-Term Energy Storage with Reversible Solid Oxide Cells for Microgrid Applications. And I'll just unpack that slightly. So what I'm going to be talking about is some work I've done using both simulation and optimization approaches. And it's especially about comparing the merits of long-term energy storage, so similar to what we've just heard about in terms of CAS, with short-term battery storage. But here we're talking about hydrogen energy storage. And the technology in particular that we're considering is these RSOCs. Now they differ from other electrolyzers and fuel cells in a few important ways. They are particularly efficient, they operate at high temperature, and they can realize both operations of power to gas and gas to power with a single device. On the other hand, they are quite an immature technology. Now, I'm not actually going to be dwelling particularly on the details of the RSOCs for this. This talk, again, is mainly just about weighing up the relative merits of short-term versus long-term energy storage. And the context we're doing this within is a microgrid type setup. So we're looking at a group of houses with embedded generation, which is solar in this case, grid coupled, and sharing energy storage, which can be battery storage or hydrogen storage, or both. A few more comments on the contrast between our battery storage and our longer term hydrogen energy storage. I think this sort of thing will be familiar to most people listening. I think the first thing I'd highlight is the cost differences, which is shown in the figure on the left. So in hydrogen storage, you have a cheap cost per kilowatt hour, so a cheap cost per unit energy, but a much higher cost per unit power. Whereas with battery storage, or lithium ion battery storage in particular, you have a sort of middle of the road cost for both. So hydrogen storage again gives you the opportunity to buy that bulk long-term storage for cheap. So the question is, how do those weigh up, those cost benefits and expenses? The other contrasting aspect, just talking big picture, I guess. Again, most people will know storage with hydrogen has a low round trip efficiency. With RSOCs, around about 35% power to power has been demonstrated. As I say, they are supposed to be more efficient than other electrolytes, and there is the prospect that we should see 70% sometime in the future, which will be quite a big leap. And there's also a flexibility aspect with battery storage, very nimble and able to ramp quickly, whereas your fuel cells are more constrained in the partial load that they can obtain and also the ramp rate. So those are the main differences which are sort of encapsulated in our simulation. So this is our setup. This microgrid, we're simulating it in AnyLogic, which is a multi-paradigm simulation software. It enables us to do quite a lot of different things. So certainly beyond the sort of results I'm discussing today, we can do things pertaining to the individual houses and their decision making and their individual finances. But for today, we're just sticking really with the microgrid as a whole, an aggregate whole, if you like. So we have households equipped with solar PV, electric cars. We have the community energy storage of either type, battery or hydrogen. And yet, to be clear, these acronyms: battery energy storage system, hydrogen energy storage system, BESS and HESS. So specifically, what we've modeled with this, we've chosen a Southeast England location, demand data from UK power networks, some irradiance data from UK ECN. 100 households. You can see here the basic vital statistics, if you like. So about 4 megawatt hours per house, basic electricity demand, and so on. I should say the electric vehicles are modeled. It's actually a similar model to the one, and indeed borrows from the one used by Rachel Lee, who presented earlier in the day. So that is based on the UK National Travel Survey, and the trips they take and the amount of charge that they need stems from that. So just an example of the sort of load and generation we get in this case study. And the plot above is for a week and below is for a year. So we can see we have a mismatch generation to supply, both on a diurnal sort of scale within a day, and certainly also across a year, summer and winter. And so that is what we're trying to address with our energy storage. The application we're pursuing is very much energy shifting, if you like. So trying to increase the reliance on the renewables on our microgrid by shifting generation to where it's needed. So these are the performance measures that we generate from our simulation, and none of it is rocket science. So the self-sufficiency ratio is just the proportion of power which is procured locally within the microgrid rather than imported. Simple payback period, that is just the estimated capex for the microgrid and all its components divided by the annual savings. And then for a bit of a more detailed assessment of the finances, we also calculate a net present value and various assumptions. And I'm not presenting the capex assumptions here, but obviously if anyone wants to ask about them, we can quickly look at them after. So what we've done is we've essentially plugged this simulation into a multi-objective optimization. So that is essentially weighing up the SSR, which was sort of using as a crude measure of environmental benefit, in that it should correlate to emissions curtailment, and we're weighing that up against the economic considerations of simple payback time and/or NPV. So we find that the more SSR we want to obtain, the worse the economics will get. So we optimize with choice of technology, in particular whether we want to install the battery, whether we want to install the hydrogen, or both. And we also size those components both in terms of power kilowatts and energy kilowatt hours, or kilograms if you like, for hydrogen. And again, objectives, SSR, or the economic ones. And before we move on to sort of the meat of the results, this is just a little illustration of the sort of storage cycling we expect to see, or we do see when we run this simulation. So this is for a system which has been designed to achieve 70% SSR. It's the cheapest system to obtain that. We can see that the hydrogen storage has very much an annual cycle, and it's a substantial amount of energy there. It's 31 megawatt hours, and the battery storage covers the diurnal cycling at 2 megawatt hours of storage. So let's move on and see how that playoff turns out between the SSR and the finance, and in particular, under what circumstances the hydrogen storage is actually selected. That's what I'm really interested in here. Where is the long-term storage the optimal selection versus just the battery storage? So the upper plot here is a Pareto front for payback period against SSR. So you can see we also have net present value plotted on the right-hand axis. So you'll see that the payback period for the microgrid starts at already touching above 20 years, and that rises more and more the more self-sufficiency you're demanding of it. So straight away we can say that the finances are not looking good for a setup like this, with the net present value invariably negative. The simple payback period definitely tending to be above the sort of lifetime you might expect from microgrid components. What's interesting, I think, is that whilst battery storage is always selected by the optimization, for this range of SSR that we've considered, so 50% upwards. So whereas the hydrogen storage kicks in at about 60% SSR. So above that SSR, the hydrogen storage is the cheapest, is always part of the cheapest system to obtain such SSR. The plot below just shows for these optimal systems how the capex breaks down. So you'll see initially the cost of the actual generation is dominant, and then as you aim for higher and higher SSR, eventually the cost of energy storage sort of gets out of control, and the cost of H2 storage in particular. Apologize for shoving a massive table in your face. So the obvious question is, how does that conclusion about needing the hydrogen storage above 60% SSR, how does that vary if we change our assumptions around? So I've actually explored 15 scenarios in total here, trying out the different bounds for the range of costs and efficiencies that we can expect. And there's no time to go into these in detail, and indeed I would suggest we don't really need to. The key point here is that for this particular microgrid, that threshold turns out actually to be very insensitive to any of these assumptions. So it stays around about 60% regardless of the efficiency of your RSOC or the costing of the different storage technologies. The things that do alter it are firstly the allowable capacity of PV that you can install. That makes a massive difference, and somewhat a higher efficiency RSOC maybe, but the PV in particular. So yeah, it definitely seems that oversizing of PV generation is a rival solution for obtaining high self-sufficiency across the year.
5 minutes.
Yeah, got it. So your long-term hydrogen energy storage, it's often more favorable just to oversize your generation if that's possible. So a natural thing then to do is to run the multi-objective optimization again and explore the Pareto fronts in more dimensions. So here we've looked at SSR payback period and PV capacity to construct a Pareto front in 3 dimensions. And what we end up with is this. So this is a projection onto the plane of SSR versus PV capacity. So we've now got certain regions where the hydrogen storage is preferred, or the battery storage by itself is preferred. Note the grey line at the bottom just shows how much self-sufficiency you get with no energy storage whatsoever. So there's certainly a large region of PV capacity versus SSR where the battery storage by itself is the best way to go. But yeah, for any given PV capacity, there comes an SSR threshold where you need your long-term storage to get further. Which is about as far as this work has got so far. So conclusions. Yes, the long-term energy storage is useful if you're looking to obtain really high grid independence and the accompanying environmental benefit. The economics are not good. They're not good even for the battery storage, the solar and battery microgrid. They're certainly not good for the hydrogen microgrid. Notwithstanding, the hydrogen storage can be the cheapest way to do what you want to do. And I think a key point is that oversizing your PV generation does seem to be the strongest competitor to using the long-term storage for a system like this. Various things we still want to do with this work. It's very much a project in progress, I think. Can we get more value from our hydrogen energy storage by doing other things with it? Rather than just energy shifting, can we peak shave? And especially, and this is a very key thing that we're going to bring in, what can we do with waste heat from the RSOC? Can we supply that to the houses? Will that make it more economical, more useful? And another aspect we want to work on is what can we do with these EVs? If we start using the EV batteries for short-term energy storage, would that make the community battery redundant? If not, how can the EVs work with the community energy storage? All right, I think I've run a bit over, but thanks for listening.
No, that was fine.
Questions?
Thank you very much. Yeah, so as usual, everyone, if you can put your questions in the chat, we've probably got time for one or two. I do have one. With the MPV calculations, have you considered setting the MPV as the target and the cost, the capex, as the variable to see what target capex you need to make the system viable?
Yeah, I think setting the NPV as an objective makes a lot of sense. I guess, yeah, arguably we should have done that, and that is probably some resource we will want to run. Yeah.
Yeah, it's an interesting one because I've encountered similar things in my own area where the MPV is invariably negative,
Yeah.
and it is interesting to see what floor you have to go to with your battery price to achieve a positive MPV. Yeah, just a comment really. We've got one in the chat. How confident are you about the future economics considering your future work themes?
So should I interpret that as, am I confident that there will be some niche for this technology once we bring in all the applications together?
Yes, that is how the questioner wants it interpreted.
I think it's hard to say. I guess that's why we're going to do the work. I think it's certainly interesting to note that various academics and experts do expect RSOCs to start to dominate over other fuel cell and electrolysis technology. Obviously, it's all about PEM mostly at the moment. But the advantage of RSOCs is that they do use cheaper and more abundant materials, and they also give you that edge in efficiency. So
Perfect. Thank you very much. I'll just jump in and say I think there's a couple left in the chat if you want to answer those directly in the chat, and we'll move on to the next presentation. But thank you very much for that. It was very interesting.
Thank you.
Okay, so on to Alyuda Ali on data-driven investigation of pressure dynamics in underground hydrocarbon reservoirs. are you ready to present? I can see in the chat, but I can't hear anything unless that's my end. If it is, someone jump in.
Can't seem to hear Aliuda at the moment.
I think they've just logged off to come back in and might be encountering some technical issues. We'll just see if they pop back in shortly. If not, we might have to skip to Donovan.
Why don't we skip to Donovan now, and that gives Aliuda some time to try and
Yeah, sounds good. Donovan, are you ready to present?
Hello, hi. Can you hear me? Yes, I am.
Yep.
Good. Before I start, I should tell you that I don't know why I always have trouble with Zoom, so please stop me, some chat message or something if there is an issue or something. Okay.
Okie doke.
Thank you very much. Just going to start sharing the screen. All right, application windows. There you go. Okay. Can you see my screen?
Yep, that's fine.
Good, excellent. Starting the presentation. Oop. Sorry. I don't know what's happened. Okay. So can you see the full screen? Just the presentation,
Yes,
right?
we can. Yeah.
Excellent, good. Okay. My name is Donovan Aguilar. I'm a PhD student at the University of Sheffield. My supervisors are Dr. Alan Dunbar and Dr. Solomon Brown. And I'm going to talk about a machine learning approach for electric vehicle availability forecast to provide vehicle-to-home services. Okay, this is an overview of what I'm going to talk about. Just a brief intro of this work, some methodology. I'm going to show you some results, and I'm going to tell you the conclusion of this work. Okay, so probably you already heard from some of the presenters today that the UK already committed to go net zero emissions by 2050, and also the ban on the sale of new petrol and diesel cars by 2030, which these decisions lead to the electrification of transport in the upcoming years, accelerating the process to do the electrification of the transport sector. But however, with the electrification of transport, the electricity demand is expected to increase in the future as electric vehicle ownership grows. So some technologies can help to reduce the electricity demand by using smart charging on the left. It's a simple diagram how it works. It works by reducing the impact of charging by charging when the electricity cost is low and off-peak times, while also providing substantial benefits to the energy consumer, such as reduced electricity bills. It also can help the penetration of renewable energies, such as wind and solar energy. And on the right, and again, a simplified diagram, how it works, is the technology called vehicle to grid. I think that some people have talked about it today. which again can provide some additional economic value over smart charging by giving back electricity to the grid, by selling it, and of course reducing even more the electricity cost for the consumer and helping the public grid at the same time. On a small scale, one of the applications is vehicle to home, which is the kind of the same as V2G, but in this case, the energy goes straight to the household to reduce the energy demand. And of course, this can lead to reduce electricity bills for each consumer, which is going to be the focus on this work. So with all these technologies, we can consider an EV as a type of energy storage system, and probably like more like a mobile battery for a household. However, in order to take full advantage of these technologies, the EV must be plugged into a bidirectional charger, and of course, the vehicle usage of each consumer can impact this availability of the EV, and of course can impact the provision of V2G and V2H services. So for this work, we ask two main questions. And can we forecast the availability of EVs to provide V2H services? How effectively V2H services can be provided as the EV availability changes? Okay, so the methodology that we use, we developed a machine learning model on Python to predict the availability of the EV, an EV, and also an optimization model formulated on Python using the Pyomo framework and the Groovy optimization solver in order to minimize the consumer's electricity bill by giving back energy to the household, by optimizing the charge-discharge behavior and giving back energy to the household when required. Okay, so in this case, we use the electricity consumption from 100 different households in London, the PV generation readings in London as well. In this case, the household has a 3.5 kilowatt PV system. And also we only focus on the Nissan Leaf 2018, which has a capacity of 38 kilowatt hour with a 0.24 kilowatt hour per mile consumption. We use V2H enabled charger with a power flow up to 6 kilowatts, and also a dynamic electricity tariff, which is currently used in the UK. The provider is can't remember the name now. Okay. Oh, I remember. The provider is Octopus Energy here in the UK, and also we also use the National Travel Survey. I think that some people already use it today to explain some of their work with this dataset. Okay, this dataset includes data on personal travel patterns such as how, why, when, and where people travel in the UK. This data was collected from 2002 to 2017 with over 4 million records. We process the data, of course, and after we filter the data, only focusing on people reported as drivers of a private car, we end up with more than 2 million records. Now, for this sub-dataset, we split it in two. The first dataset, we clean the dataset and we end up with 1.9 million records. from just 2002 and 2016. From this data set, we use 80% for the training set for the machine learning model and 20% for the test set. Now, the second data set, again, we clean it and we end up with 55,000 records. This is only focusing on 2017, the most recent year reported on the survey. We use this data set as new instances and to collect the vehicle usage profiles that we were going to use on this work later on. Okay, so this is an example of the data after cleaning the full data set. This is an example showing the unique ID, the travel day of the week. In this case, it shows as 6, which is Monday is the first day of the week, and Sunday is the 7th. So in this case, this person traveled on a Saturday. It shows the starting hour, the starting minute, of course, the starting time, the end time, and the journey number during that day. For example, in this person traveled 5 times during the day, and the trip, the starting location of the trip, you can see that it started at home, then it went to some sort of activity, sport activity, then from sport activity it went to work, and then from work it went to home, and then from home it went for entertainment, and then from the entertainment it went back home. And finally, at the very right, you can see the trip distance in miles for each trip. So the vehicle usage categories, we divided in 5, very low usage, low, medium, high, and very high. You can see how we split them. We use 100 profiles per category. With at the bottom, you can see an example of the dynamic tariff that we use compared with a fixed price tariff. For the machine learning model, we divided the model in 3 parts. The first part is a classification problem to predict the start location. The second part, a classification problem again to predict the end location. And the third part, a regression problem to predict the total distance in order to calculate the energy consumed by the EV. Okay, these are the results. I'm going to start showing the results. The results for the machine learning problem, for the first part, which predicted the starting location, we got a score of 86% accuracy. For the second part, which predicted the end location, we end up with a 85.88, almost 86, just a tiny bit less than the other percent accuracy. And for the third part, almost 79%, over 78%. So once the vehicle availability has been predicted, the charging strategy for the EV was optimized. Here are the results. At the top, it's the very high usage profile, showing the first plot shows the house demand in blue. Hope that you can tell the difference from the colors. Apologies if you can't. The PV generation in yellow, the demand when the EV is available, and also the demand when the EV is not available. The plot at the bottom, just at the bottom of that one, is the availability profile for this particular user, the one that we predicted and generated. Just for comparison, at the bottom half, you can see the very low usage profile and how the availability profiles vary between each other. Again, the same house demand, PV generation, the demand when the EV is available, and the demand when the EV is not available. For these plots, if the demand is positive, it's when the EV is charging or when the house requires some demand, and when the PV is generating. For the negative is when the EV is giving energy to the house or consuming for travel. Here is the SOC, again for the same profiles. On the top, the very high usage profile. You can see how it charges when it's available, and this discharges when it's in use by traveling. And just, I don't know, the person arrives to the shop or whatever and then stop using it, so it stays flat for a couple of hours, and then until it gets plugged again at the household, start charging. And again, the same for a comparison, the very low usage profile at the bottom half. Again, this is just for comparison. This is the full data that we got. Again, at the top, house demand, PV generation, demand, and when the EV is available, demand when the EV is not available. The second plot is the SOC. The third plot is the EV action, if it's charging, discharging accordingly. And of course, at the bottom, just as a reference, the availability profile for each one of these users. This is just the general results that we got. I'm going to explain them in the conclusion. Oh boy. Okay, I think that, did my slide change?
No, it doesn't seem to be responding to you.
Oh boy. Okay. Just give me a second. Oh, there you go. Just change, I think.
Yep, that's fine. 5 minutes
All
by
right.
the way.
Okay, excellent. So the conclusion for this work, of course, as you might already imagine, the less an EV is used for traveling, the greater its availability to participate in V2H services. From all the categories of EV user, all the categories of EV users benefited from reduced power bills when deploying V2H services, of course. There is an electricity cost reduction of at least 46% on average when V2H services are provided. Of course, this is only with the dynamic tariff. We didn't use any other. And most importantly, this is regardless of the level of vehicle usage. So it doesn't matter if you just use it once in a while, just going for the shop or whatever activity you want, or if you are commuting every day and you have a very active life. Well, probably not now because of the lockdown, but okay. Even the most frequently used EVs were available for V2H, were available to provide V2H services at least 60% of the time on average. So, which means that, again, regardless of the amount of times that you use your EV, you have a very high chance to benefit from this technology and reduce your electricity bill. Okay, that's my last slide. I'm not changing for the other one. No, that's my last slide. Anyway.
Cool. Very much. That was really good.
Yeah, thank you.
Any questions in the chat, please? I do have one. What impact do you think participating in this would have on the life of the vehicle battery, and how that might be dealt with as well with the warranty potentially on that battery?
That's a very good question. Actually, I didn't add it to the slides, but future work would be to consider the degradation of the battery, the impact of the degradation of the battery, and yeah, the degradation of the battery, and yeah, the guarantee depends from each dealer, I think.
Yeah,
some dealers, as I don't know, Nissan, they assure that even if you engage on these V2G activities, there is still some warranty over there.
Okay.
And also some energy providers are opening some sort of programs where they provide you the car, and it depends on on your dealer, I guess. Yeah.
Perfect. Thank you very much. Right. Well, we'll move on to try and get to time. But if anyone does have any further questions for Donovan, please pop them in the chat, and I'm sure he'll get to you as quickly as he can.
Right. Thank you very much for listening. Bye.
Thank you. Okay, Aliuda.
Yes, I'm ready.
Okie doke. If you just stop, there we go. Donovan, stop sharing. Away you go.
Right, thank you. I've got some challenge, but I'm back. My name is Aliuda Ali, and right. I'm Aliuda Ali, and I'm here to present this presentation titled Data-Driven Based Investigation of Pressure Dynamics for Underground Hydrocarbon Reservoirs. And I'm from the Department of Automatic Control and Systems Engineering, University of Sheffield. This slide is my outline, which I will start with background and motivation. Under this, I will talk on the role of underground gas storage, the problem we're looking at, existing methods, and the aim of this study. I will also talk briefly on the materials and methods employed in this work, which include numerical reservoir simulation, which serves as the reference model, and then dynamic mode decomposition, which is the data-driven based approach we are advocating in this work. I will talk on resource and discussion, and then I will end this presentation with conclusion and future work. Next slide, please. Background and motivation. So now first, the role of underground natural gas storage. One of the role of this type of facilities is meeting the seasonal consumption. It requires sufficient time to explore, produce, and transport natural gas. And most of the time, the produced quantity is not needed when it arrives its destination. So to preserve that excess quantity, it has to be stored via injection into underground storage facilities. So, and during a time of raised demand, this type of facility ensures that the raised demand, especially in winter time, is met. So it's a kind of providing a security against unanticipated energy supply interruptions. And then another thing is this type of storage also provides a larger and safer storage. I think other previous speakers have stated some points on this. So this is underground formations. They accommodate natural gas at high pressure, and that makes them kind of larger storage facilities and a bit safer as compared to storing such kind of product on the surface. And then here we are looking at these type of facilities, the subsurface formation. They are classified into three major categories, which include depleted hydrocarbon reservoirs. That is what we are looking at in this work, and then salt caverns, and then aquifer reservoirs. So looking at their daily deliverability by storage type, depleted hydrocarbon reservoirs has the highest percentage globally, and then followed by salt caverns and then aquifers. Also, apart from providing larger storage and deliverability, depleted reservoirs also are considered economical due to their known geological properties in comparison to salt caverns and aquifer reservoirs. Next slide, please. Now, the problem we are looking at is the challenge of learning pressure dynamics or pressure variations during natural gas storage or injection in this subsurface storage. So existing methods entails working with complex and cumbersome algorithm and then carrying out numerous simulations, which is time consuming and also difficult to maintain or to upgrade. Next slide, please. So the aim of this work is to develop a data-driven model that learns and reproduces the pressure dynamics of an underground storage reservoir model as natural gas is being stored or injected into the reservoir. Next slide. Now, materials and methods. First, we look at simulating a reservoir model numerically. And we consider this is a reservoir model we adopted and modified from the first Society of Petroleum, that is SPE, a Society of Petroleum Engineers, first comparative solution project. We set up a reservoir model with an injection well and production well. So it is a three-dimensional, three-layer reservoir model with injection well completed in the first layer, and then we have a production well completed in the third layer. So this first figure depicts the porosity distribution within the reservoir model, which is uniformly distributed with a value of 0.3. And this figure is showing the permeability distribution within the reservoir model, which we consider heterogeneous distribution, where the first layer has 500 millidaki, and then the middle or second layer, we assign the value of 50, and then the bottom layer has the value of 200. So the reservoir model initially is undersaturated with no free gas inside, and then we assigned, and with initial pressure of 330 barometric pressure, and then we assigned a bottom hole pressure to the injection well to enable natural gas injection. So a kind of, we assigned 560 bar to the injection well, and we simulated this reservoir for 1,200 days in 120 time steps. So the aim is to generate a kind of spatiotemporal database that contains the pressure field information as natural gas is being injected into this reservoir, and then to apply the proposed data driven into the pressure field data of the reservoir, and then to see how well that data-driven approach will do in reproducing and learning the pressure dynamics of this subsurface storage facility. Next slide, please. Now, this is the data-driven approach, just a brief about it. So now, having simulated the reservoir numerically and generated the data, the pressure field data were retrieved, and then first they were arranged in two matrices, Y and Y prime. So these are snapshot matrices. So dynamic mode decomposition, or DMD, attempts to construct a linear dynamical system that is having Y at time t to approximate Y at time t plus 1. So here, if we see, we have a matrix A here, which serves as a least square fit solution for the approximation. So the major task here is to solve for this matrix that will give approximations of this pressure field data at time t plus 1. So This site is just a summary of the steps involved in this data-driven approach. First, singular value decomposition is performed on matrix Y, and then R here is the rank of truncating this matrix. So performing this will yield 3 matrices, as we know from linear algebra. So you have matrix U, S, and V. So the elements, the diagonal of matrix S here contains the singular values of Y. So next is to obtain the full matrix A. So here, this equation is simply solving for A, or solving the pseudo inverse of Y to get a full matrix A. So when we get the full matrix A, the interest is on the leading eigenvalues and eigenvectors of A. So with that, we compute A tilde, which is the least square fit, that is projecting matrix A onto the POD modes, that is U, then to get A tilde. And then next is computing the spectral decomposition of A tilde. So with this expression here, this matrix W here, the column of this matrix W contains the eigenvectors of A tilde, and then the diagonal of this matrix here contains the DMD modes of the reduced system, or the lower dimensional system. So with this information, with the eigenvectors and then the DMD modes, the full state pressure field can be reconstructed using this last equation here. Next slide, please. So results and discussion. First, we look at the numerical simulation of the reservoir model that was set up. And after performing the numerical, the simulation for 1,200 days, we observe how the pressure evolves within the reservoir model. So initially we have 330 within the reservoir as initial pressure. So as natural gas is being injected within the formation, the pressure keep rising, and at the end of the simulation period, the pressure raised to about more than 480 bar. So that happens as the formation accommodates the injected natural gas and making it such a kind of pressurized container. And then it is also worth mentioning that the production well is to be closed. We just want to observe what happens as the formations accommodate the injected natural gas. And also to get an insight of what is happening within the grid cells, we plot some snapshots of some selected days from the time that the simulation commences. So day 1, day 65, day 190, and after 422 days, that give us the idea of the pressure evolution within the pore grid cells or within the reservoir formation. Next slide, please. Now, we now apply the DMD algorithm on the pressure field data and then follow all the steps mentioned previously. And then we compare the results of the DMD with the reference data. And then that is what we obtain in this first figure. We have a very good match, and DMD was able to reproduce the pressure field or the pressure dynamics of the simulation as natural gas is being injected. And not only reproducing, DMD can predict one time step ahead. And then it is also worth mentioning here that how the number of agent vectors retained for the reproduction or for reconstruction of the pressure field data. So in this case, 15 agent vectors were used to reconstruct the pressure field metrics or data. And then the other side is the pore pressure variations. We compare the DMD outputs with the reference data for the selected days shown previously in figure 4. And DMD also show a good agreement as regards capturing the pore pressure variations as natural gas is being injected within the formation over time. Next slide, please.
5 minutes.
So this is what we have for now. And in conclusion, a data-driven method that learns and reconstructs a pressure field of a depleted reservoir model that mimic the storage of natural gas in subsurface formation is proposed. And based on result, we have shown that the method is able to approximate the reservoir pressure change over time with a root mean square of 2.9886 and R square or coefficient of determination of 0.996. As part of our future work, we are experimenting on different type of rock properties, that is changing the porosity and permeability to see how it affects the results. And then also we are considering, after storing the natural gas, then we open the production well and then see how the pressure behaves as the reservoir produces the injected gas, and also see how DMD will do in terms of learning the pressure dynamics when the system produces. Next slide. That's all for now. Thank you for your attention.
Thank you very much. Very interesting. Does anybody have any questions? If so, please put them in the chat. If not, we might just jump straight to the break as we're 2 minutes over, and I don't want people to get angry that I've not had a chance to get their coffee. Any questions? No? Well, if you keep an eye on the chat, Aliuda, and if anyone has a question, I'm sure you can respond to them directly. But thank you very much for that.
I will, thank you.
And thank you everyone who's presented in this session. Some really good presentations there, really interesting stuff. If we reconvene in 7 minutes at 20 to 3.